In this video, I'll be building a simple homebrew computer from scratch, like it's 1995. Why? Well, I just want to play more with hardware, and explore things on a lower level than you're normally able to do on a computer. So, what exactly am I doing in this episode? I'll be designing a PCB or PCBs that I will get etched and assembled. I'll make a boot ROM for it, which will allow me to push new code to it over a serial port. And by the end of the episode, I want to be able to write a hello world program in C that I can run on my little computer. So let's start with the hardware. To keep things simple and slightly more realistic, I'll limit my selection of chips to what I can find in this catalog. First, I need to select the CPU. There's a whole bunch of things to choose from. Z80, Intel 8088, 6502, 68000. I think I want something a bit more capable, like a 16 or 32-bit CPU. Between the Intel and Motorola ones, the 68000 is a lot nicer to program, and it has a fairly nice electrical interface. The 68000 isn't fast, but I'm mainly concerned about the real-time performance and not the computational performance. To keep things simple, however, I've been advised to use an 8-bit data bus. The layout can get quite messy with a 16 or 32-bit data bus. So I'll be using the 68008, which is a 68000 with an 8-bit data bus and a 20-bit address bus. This will further tank the performance to the point where it might as well be a rounding error, but it'll do. The 68000 architecture was quite popular in the demo scene, and it was frequently used at universities in their computer science courses at the time. So information about it is not hard to get, be it online or offline. To go with this, I'll use the 68901 multifunctional peripheral. This will give me a serial port, some timers, and an interrupt controller with 8 external interrupts. I'll also get a 32KB static RAM, and I'll use a 32KB EEPROM for the boot code. As bus glue, I'll use the National Semiconductor's GAL16V8 programmable logic chips. These were quite popular among the more advanced hobbyists, and the Electron magazine ran quite a few articles on them. The idea is that I'll be able to expand this computer with more interesting peripherals in future videos, but we'll start simple. So, now I need to design this thing. I'm going to design it on my computer. In a previous episode, I used a freeware DOS program to do the schematic, and a demo version of ProTel for Windows to do the layouts. This setup was kind of insane, but I'm pleased to report that the latest Simtel shareware CD-ROM contains a better option. A demo version of PADS, both the schematic program and the layout program. So I'll use this instead. It has some limitations on the complexity of the design that it can make, but at least all the features are available, like the library editor and saving in general. But it's a much more complete package, and hopefully it won't be as janky to transfer the design from the schematic to board with it. Make no mistake though, PADS is the kind of program that absolutely requires you to read the manual. Without the manual, you'll be completely lost. These limitations does affect how I design this computer. I'll basically have to break it out into smaller separate boards, as I won't be able to put everything on one bigger board with this demo version. The core computer will consist of 3 boards, a CPU board, an MFP board, and a boot board. There is also a 4th board that will be useful in the beginning, which I designed off camera to get some practice with PADS. To make this computer easy to build, I'm making these boards single layer. This will negatively affect signal integrity and power delivery, but I'm sure it will be fine. One of the first things I need to do then is decide how I connect these boards together. I want this interconnection to be the processor bus with just enough glue to fit everything else in. I wanted to use a 40-pin ribbon cable, so I start out by defining what signals I want on it. Normally, this is an iterative process, where layout work influences the final pinout. I'm not masochistic enough to iterate this in PADS, so I've already built a prototype with modern tools to find a workable pinout. With that done, I can start making the symbols I need that aren't in the library. For the boot board, this is the SRAM chip and a GAL. PADS has a fairly easy to use interface for creating simpler symbols. I start out by filling out some electrical information, like the name and footprint of the part and the hidden signal pins, if any. For this SRAM, I add the power and ground pins as hidden pins that are automatically connected. Next is creating the actual symbol. I can just let it automatically create a box and place some pins. I just need to tell it how many inputs and how many outputs I want. Next is assigning names to all pins. This will make it easier to number them later. For pins having a name ending in a number, you can just continue clicking and it will automatically increase the number. Same for assigning pin numbers. I can just start with pin 1 and click on them in order, each getting the next number up. Finally, some of the input pins are active low, so I go into the Change Decal menu, allowing me to give them an inverted signal look. The gal is a very basic symbol, so I'm not gonna spend much time talking about that. If I was really ambitious, I'd make one symbol per program gal with proper pin names and such, but not this time. The basics of pads is that commands are chosen with the function keys. That's how you navigate the menu to the left. There are also some typed commands. These offer no feedback if they worked or not. Panning the view is done with the numpad, with numlock turned off. With that, I can start drawing the schematic. It's a really simple board, just an SRAM, a ROM and a GAL for glue logic, and the IDC connector for connecting it to the other boards. The idea is that the computer will boot from ROM, copy the contents of ROM into the SRAM and then mirror the RAM down to where the ROM was in memory. There is also a jumper for enabling boot from RAM, meaning I can bypass the ROM entirely. I'll explain why I've done it this way when we get to the software. It's also worth noting that I haven't mapped the address lines or data lines one-to-one here. This greatly simplifies the layout, and for the SRAM it really doesn't matter where the address lines or data bits go. For the ROM, this makes a difference, but I can fix this in software later by scrambling the ROM image before programming it to an EEPROM. Now I need to transfer the schematic to the PCB layout program. This is not very intuitive. I haven't found a way to import the schematic into the layout program in a way that brings in nuts and components. I can export an ASCII file, and the layout program can do ASCII import. This does however just blow up on import. No, what you do is that you go to Reports and Netlist and export a netlist. Then, in the layout program, you import an ASCII file, but not a netlist. This will bring in the nets and the components. This was helpfully not mentioned anywhere in the manual I got, as it was split up in separate manuals for the two programs. I suppose that's what service contracts are for. Now I start out by drawing the outline of my PCB. I got 100 by 75mm laminates, so I'll make a box that is 3.9 by 2.9 inches. Then I can start placing all the components. As I can't have the schematic open at the same time, I'm a little lost as to what is what, but with the chips out I can figure out the rest. With that I can start clicking out the traces. By setting the grid to 25 thou, and having general design rules of 12 thou wide traces with 12 thou spacing, and all through-hole components having a pin spacing being a multiple of 100 thou, the layout itself isn't very cumbersome. What is a bit more cumbersome, however, is that pads is one of those EDAs that expects you to route between the exact two pins that it asks you to. You can't just connect a pin to the nearest other thing of the same net. If it wants you to route a pin to the other side of the board, then that's where it goes. If it wants half of your power pins to go to the other side of the board, then that's what you have to do. If you want them to use the same traces, then you just have to route it in the exact same way that the previous pins were routed. The manual even calls this process copper sharing. Worse is that if you need to move this trace later, then you have to move all copies of said trace separately. Anyway, I finished the board by clicking out some copper fills that will make etching easier. Again, you can't just do a flood fill and let the program figure out where the copper plane can go. You have to click out each polygon one corner at a time. And since you can't easily view what net each trace belongs to, creating ground and power planes isn't as easy as it should be. Before taping out all the production files, I do a final check that I haven't accidentally connected two nets that shouldn't be. I only get 3 errors, one per mounting hole that the plane touches. I'm fine with this, so I proceed to tape out. This is done through the CAM menu. I need to output the copper artwork, silkscreen and drill templates. I want these in 2 different formats, PostScript for a laser printer and HPGL for a pen plotter. I'm not sure if I'll have a use for the silkscreen, but I might as well output it. I also go back to the schematic and output it in these 2 formats. From the schematic program I also export a BOM. Anyway, that's one of 3 PCBs done, so I jump straight into the next one. For this one, there is another chip I need to draw, the multifunction peripheral chip. Unlike last time, I'm not going to use the simplified symbol creation. This thing's complicated enough that I need more structure. But it's really no harder than clicking out the pins you want roughly where they go, followed by a rectangle. And from here, it's just like the other symbols we've already seen. Name each pin, then set the pin numbers. Finally, add the pin decals for things like clock inputs and active low signals. I also had to make an oscillator symbol for use with the existing oscillator footprint. This board isn't all that complicated either. I need to connect the chip up to the bus connector and add an RS-232 transceiver for the serial port. This MFP will also provide a few timer interrupts for the software to use, as well as an interrupt controller with 8 external interrupts. As I don't have the space for them on my main bus connector, I dropped them off on my 10-pin IDC connector for a future bus adapter to use. The GAL on this board does have a fairly important task, however. It's responsible for generating the data acknowledgement signal to the CPU, basically telling the CPU when the bus transaction is done. I put it here because the MFP chip generates this signal when you access it, but nothing else on the computer will. So this is where I will merge that with the generated acknowledgements for everything else. I'm setting it up so that everything in the lower half megabyte of the 20-bit memory space has two wait states, except for MFP access, which uses the provided ACK signal. The upper half megabyte has no wait states and is for a future RAM expansion. However, as I'm making this schematic, something unsettling happens. As I try to place power symbols, it starts asking me for a net name. As I try to route the trace, I notice in post that it lists a net name P instead of the normal generated ones starting with $2 signs. I first think this is a problem with the capacitor symbol I'm using, but it's been fine before. As I route these electrolytics for the MAX232, I notice how the net names for these as well is just the letter P. I don't catch on to something being very wrong until I try to route the bus. This is when I decide to save and restart the program. After a restart, it all seems fine again, and I can route the bus without any problems. The power symbols act normal again. Crisis averted. We'll get back to this. I quickly finish the rest of the schematic and enter the PCB layout program. Just like we saw before, I start with the outline and then start placing out the components. But something's not right. The electrolytics aren't connected to anything. I first think it's a library symbol issue, but everything looks fine. In utter bewilderment, I try removing the connections and adding them back again. To my surprise, this seems to fix it. I now start to worry that this is some kind of resource limitation with the demo version regarding how many nets or line segments in the schematic I'm allowed. But at this point I figure there's nothing left but to start layout work. Until I realize I'm missing a capacitor, so I go back into the schematic again. I had also wired stuff up incorrectly, but again, back into the PCB editor. As I place everything out again, I notice I've forgotten to connect the ground pin on the serial port. So, back to the schematic again, fix this little stupid mistake, export a new netlist, and back at it in the PCB editor. I should probably mention that I have yet to find a way to update the board netlist from the schematic. If you try to re-import the netlist, it will just complain about the duplicate connections until it gives up due to an excess of errors. So every time I've made a change to the schematic so far, I've had to start over with the PCB layout. This time I'm pretty happy with how it looks, so I'm committing to doing a full layout with this netlist. But after working with it for a few hours, I noticed something. There's more missing connections. The serial port isn't even connected from the MFP to the transceiver. In the schematic, everything looks fine, it's connected. But this, again, is probably from when the schematic editor went into a weird state and started routing off-screen nets named P or something. So once again, I'm starting over. After spending another 15 minutes or so, I find the next couple missing connections. I'm getting quite sick of this Sisyphean task at this point. Instead of making a small change to the schematic and starting over with the layout, I'm just gonna create my own small little netlist. One that includes the new nets to add, without all the existing ones for the program to choke on. And that worked. I can continue my layout work without throwing this past half hour away and starting over. Less than an hour later, I find even more missing nets. I don't know if it's a bug or a feature in the schematic capture program, but it sure is causing me some trouble. Pushing on for a few hours and a half dozen more missing connections, and it's starting to look good. It's time to tape this one out as well. Last, it's the CPU board. For this, I also need to make a footprint for my reset button. Thankfully, the mechanical dimensions are available in the catalog, so I can draw it based on that. This isn't too hard either, just plonk out the pads and draw a silkscreen outline. One quirk here is that you seemingly can't have two pads with the same number. These buttons have two pins connected together on each side of the switch, and you normally want to make them the same connection on your PCB. That won't be possible here with the standard library symbols, but I'm okay with only using one set of the pins. Finally, I need to create the library symbol for my 68008 CPU. This too I make myself without using the automatic symbol creation feature, as there's quite a bit of complexity to this symbol. But with that done, I can start working on the last board. This too isn't going to be too complicated. There's the CPU, a gal for glue logic, and a 555 to generate reset pulses. This board basically just brings out the CPU bus out on the ribbon cable. The glue logic doesn't do a whole lot, but one important task is to decode the CPU function code output, to generate the interrupt acknowledge signal for the interrupt controller in the MFP. You could theoretically decode this with a free input NOR gate, and let the output go into the VPA input, in order to auto-vector interrupts without using an external interrupt controller. But since the MFP already gives me most of the bits I need, I don't see why I'd go for an inferior solution. This feature where the schematic program suddenly stops assigning nets correctly happened twice while I was making this board. I don't think I did anything special to trigger it, so I don't really know what this is about. There isn't really much more to say about this, we all know the drill now. Layout wasn't all that exciting either. This is the simplest layout of them all, requiring 0 bridge wires. Quite time consuming though, this was about 3 hours worth of layout work. No major drama though, and I didn't even have to start over once. Aside from the mystery 4th board, that's all the PCB design done. Before I get these made, I can now look at how to program the gals. A gal is a simple type of programmable logic. You have the following logic available per output. Each input pin is available both as a regular buffered input and an inverted input. These then go into a huge AND matrix, where you select which pins get logic ANDed together. One or more of these AND terms then get ORed together. The result can then optionally be inverted with this XOR gate. Finally, there's an optional D register that the result can be clocked into. The chip can operate in 2 modes, registered or complex. In registered mode, 2 inputs are reserved for a register clock and an output enable. In complex mode, these are available as regular inputs. In complex mode, you can't use registers, but you can still control the output enable of each pin. Most, but not all outputs can also be used as feedback into the equations. So, let's start with the boot ROM gal. You program these with a so-called equation file. The first line is a free text description of the design. This is then followed by a declaration of which type of logic chip is used, in my case a GAL16V8. I then list the names of all pins in the order I want them allocated. I put them in 2 rows to represent each side of the DIP package. These are then followed by the equations keyword, and below that all the equations. There you assign each output to some type of input. The colon equals means it goes into a register. The regular equals means it's just combinatorial. Here you just list all the terms to be ANDed together, using an asterisk to represent AND or multiply. These are then ORed together, represented by the plus sign. The slash means inverted. You can freely mix inverted and non-inverted inputs and outputs. It'll work out automatically where to actually invert and where not to. And while I'm editing this video, I'm noticing a mistake. This LL output is used to keep track of if the SRAM is mapped into the location of the ROM. The idea is that a memory write to a ROM address will flip a switch to mirror the RAM down to the ROM address range, overridden by a jumper that always mirrors the RAM. Without this, the interrupt vector table would be permanently burned into ROM and won't be changeable by software. But this AND sign is supposed to be a plus. These are 2 separate terms. This file is then compiled to a JADEC bitstream with equation to JED. Aside from the JADEC file, it also produces a report with a summary of what it understood as well as a graphical pin map of your chip. Anyway, onto the MFP glue. This one isn't all that special at all. There's a chip select generation term to select the MFP, and you might be able to tell that I placed it at 10,000 hex, just about the 64K of RAM and ROM. The rest of these signals are just the data acknowledge generation logic. D1 and D2 are used to delay the signal 2 clocks, to generate the 2 wait states. I generate the JADEC file, but I notice my interrupt acknowledge pin is unused. It's important that we don't generate data acknowledgement cycle when an interrupt is being processed, as this is a job for the MFP. So I add that guard into the equations. But with that fixed, it looks good. Finally, the CPU glue is basically just there to identify the interrupt acknowledge cycle from the CPU. I also abuse it to bridge a few signals instead of using jumpy wires. And finally, this is what a JDEC file looks like. But with that, I now have everything I need to make this thing. Which brings us to this video's sponsor. My friend up north. I don't want sponsors. I put all the production files on these floppy disks. So, let's head north. Last time around, I had a dot matrix printout that I photocopied to a transparency, which we then exposed the PCB laminate with. Since I have smaller traces packed more tightly together on these boards, we'll be using a pen plotter. As warm-up, we started off with plotting the schematic on A3 paper. Sorry, wrong clip. The pen plotter accepts commands over a serial port, and it doesn't need anything more advanced than the terminal that comes with Windows 3.1 to run. Here it's set up with macro buttons for all the initialization operations needed. To start the plot, we just send the HPGL export I got out of pads. The plot sequence starts with a calibration dance. Afterwards it grabs a pen and starts drawing lines. In this case with a slightly modified ballpoint pen. This particular plotter can hold up to 8 pens. The clicking you hear is the solenoid that puts the pen down onto paper. The paper is held in electrostatically and is attached quite well despite the steep angle. The program generating these plot outputs needs to know in advance what pens will be available. I configured pads to only expect a 0.3mm pen in slot 1, so these bus connectors and the bolt fonts is done with multiple passes. So when we were about to plot the actual PCB artwork onto the transparency, we ran into trouble. He had some nice 0.3mm plotter pens that could do transparency plots, so we used one of those. Look at the lines out in the ground plane hatch, they look pretty crisp and dark. Then look at the traces in the middle. They are all smudged out and light. The pen was flattened and effectively destroyed in this plot. So we needed a plan B. We tried some other pens on the transparency, but it's a pretty unforgiving surface that nothing would really stick to. After digging around in the drawers for a bit, we tried using a ballpoint pen on tracing paper. This looked like a decent shot at making it work. There's a bit of smudging and the traces are a bit thin in places, but the contrast is good. So, onwards to etching! As I'm using single-sided boards with photoresist on, step 1 is to transfer the artwork from the tracing paper to the board. This is done with UV light. To start off, the UV tubes are heated up for a more uniform glow. Especially around the edges, the tube can be quite weak with cold tubes. The ink side is up, and on top of this the board is placed with the photoresist facing down. The areas exposed to the light will degrade, while the areas protected from UV by the ink will remain intact. We had to adjust the exposure time to 4 minutes instead of the 3 used with transparencies. And the board was scooted over a bit after 2 minutes for a more even exposure. After this, the board was washed in a weak lye solution. This will dissolve the exposed photoresist. This is why a good dark print is important. You want the exposed parts to be degraded as much as possible, while the protected parts should be as untouched as possible. After gently cleaning off the exposed photoresist with a sponge, the board is transferred to the etching tank, filled with warm sodium persulfate solution. Conveniently enough, the etching tank and all of its content was already there from last year. We just had to top off the water level and turn it on. No need for the forbidden Dr. Pepper this time. Less conveniently though, is that the etching solution was quite saturated at this point, and it took an hour for the etch to finish. After replacing it, the etching time went down to 5 minutes. For this one, we forgot to preheat the UV tubes, so it got a bit underexposed at the top. When the etching is done, the board is rinsed off in some cold water. Lastly, the holes are drilled. Most holes were supposed to be 0.9mm, but after seeing how little copper was left, we went with 0.8mm drills. I say drills as 2 of them died in the process. Finally, some deburring and scrubbing with acetone and steel wool. This removes the rough edges and strips away the remaining photoresist from the copper. As a final thing, we got the silkscreen layer plotted on some paper. I'll glue this to the board later. We tried putting the whole board in the plotter and have it draw it with a marker, but the 1.5mm board was just a tad too thick. With the boards made, it's time to program the gals. I don't have the equipment for it, but my friend here does. Before we begin, we get some labels printed out. Afterwards, we can switch the parallel port over from printer to the ROM burner. A high-low systems all 07. Programming starts by selecting the manufacturer and model number of the chip. While these gals were cloned and fairly universal in their function, you still needed to know exactly which one you got. So if you got a bunch of gals marked National Semiconductor off eBay, but they were actually relabeled VLSI ones, program would fail. Ask me how I know. Programming them isn't any harder than loading the GED file that equation to GED generated. From there you just hit program and that's it. And before we forget which chip is which, it was labeled. You can tell this chip programmer was built for production use. It has status lights search on the device itself, as well as a button to start programming the next one. But that's it. It's time for me to go home and build a computer. First, I'm going to apply the silkscreen plot to the board. I cut it out by using the PCB as a template. To the paper cutout, I apply a bunch of glue with a glue stick and then place it on the board. After the glue has dried, the holes can be cleared out by holding the board up to a strong light source and poke at the holes with something sharp. As I start soldering these boards up, I quickly discovered what a horrible idea the IDC connectors were. The slightly wonky hole pitch from manually drilling the holes, combined with the 0.8mm drill being too small for the pins, meant I just couldn't get the connector in there. After checking that the connector pins weren't made of anything too toxic, like beryllium copper, I tried filing the pins down. But I just couldn't get this working. So I changed plans. I took a regular straight 40-pin connector and soldered a bit of stripped wire wrap wire to it. This I could then thread into the board. Once I had the lower layer in place, I secured it to the board with superglue. After which I soldered the second row in place while trying not to breathe in the fumes from the burnt superglue. You'd think the large CPU package would be a problem then, but it wasn't that bad. You had to guide it a bit, sure, but with some fiddling I got it in there. It took like 20 minutes in front of the camera, but at least it was possible. This CPU might look big, but it's still nothing compared to the Texas Cockroach, which is the 68000. No, the worst part about assembling these boards are all the imperfections left by the ballpoint pen. Traces ending just before the pads, and the fuzz and splotches characteristic of a ballpoint pen covered in lint. I spent about a week putting these boards together, and I spent about 10% of that time actually soldering components in, with the rest being an even split between troubleshooting and fixing defects on the board. But I got the board soldered together now, so it's time to install the gals. I put these in sockets as I may want to reprogram them in the future, in case of bugs or new features. The final empty socket on the boot board is for a boot ROM, which will contain the startup code. Right now, however, I don't have one of those, as the boot monitor software doesn't exist yet. So I'll be shorting this SRAM boot jumper instead, which will mirror the SRAM down to the ROM memory space. So, I've built this thing. Now what? Well, the software doesn't exist yet, so I guess I better get started with that. This actually started all the way back when I was reinstalling Linux on my computer. When I had the development tools installed but nothing else. I had to do this with the maximum amount of disk space available. I need an assembler, a linker, and a C compiler. Remember, the goal is to run a Hello World program written in C on this thing. So I start by compiling the GNU binutils package. Normally, it would generate code for the platform that you're currently running on. With a switch to the configure script, however, I can tell it to target the 68000 processor with a COF binary executable format instead. I would have used ELF, but it wasn't supported for 68000 in this version. This grinds on for about an hour until it's time to install it. I run out of disk space. Like, I got 0 blocks left, I've used it all. But I was able to delete and rearrange some stuff to squeeze binutils into opt, where I stripped the binaries. I now have a working assembler and linker. Time to get the compiler. I'll be using GCC 2.7 for my cross compiler, released in mid-95. A cross-compiler is just a compiler that compiles code for another platform than the one you're currently running. Before starting the compile, I try clearing out as much of the build tree as I can. There's megabytes to save by removing files I won't use in the compile. I glance into the included documentation for clues about how to build a cross-compiler, but like binutils, it's pretty straightforward. I only enable the C compiler as I don't know the other languages anyway. And again, now we wait as it crunches along. GCC itself didn't take too long to build, about 45 minutes or so. Worse was libgcc, the support library. It wouldn't build at all, in fact. It expected a C runtime to be in place for the target, which I don't have. So I ended up creating some dummy headers with a declaration it appears to want. This was a slow process. Each compilation attempt took 20 minutes. But after much trouble, I was able to get this thing installed, with about 340 kilobytes of disk space to spare. With the tools installed, I can start writing code for my little computer. But how do I load the code onto it? That's what the mystery fourth board is for, my so-called bus probe. When the processor is in reset, I can access the memory as if I was the CPU, which allows me to read and write to memory. That way I can upload code, try to run it, and then read memory back to see if it worked. I implemented this using these shift registers, which allows me to control the 68K bus using my parallel port. Before getting into the software, I guess I should spend a few minutes talking about the Motorola 68K bus and how the CPU talks to the other chips. So here's a map of all the signals of the 68008. Clock drives the timings of everything, but the bus itself isn't strictly synchronous to it. The FC0 to FC2 outputs tells us what type of bus transaction it is. This is also how you differentiate between a user mode and a supervisor mode access in an external memory protection unit. This is also how you know if the CPU is requesting a vector number in response to an interrupt, which is a CPU space request. I don't use the 6800 peripheral control lines, so we can ignore them. I'm also not really using any of the system control lines. Bus error is used to signal that a transaction failed, be it because the memory doesn't exist or that you don't have permission to access it. Triggering this is what generates segmentation faults, but I'm not using it. I do use the reset input, but only for the reset button. The halt line is bidirectional. A serious system fault can pull this line low to stop the CPU, and the CPU can pull this line low when it crashes in a way that stops code execution. I've connected it to an LED, but that's all I do with it. IPL controls the current interrupt priority level. Changing this to a higher priority level triggers an interrupt, with 0 being no interrupt. The bus arbitration signals can be used by DMA controllers and such that need to take control of the bus for a short while, which I'm not using. The async bus control signals are the most important ones. DTAC, or data acknowledge, tells the CPU that the transaction is done and that the CPU can finish its request and release the bus. Data strobe means the CPU is trying to read or write memory. R/W tells the system it's a read or a write. A high voltage here means that it's a data read. A low voltage indicates, as the overbar shows, that it's a write. The overbar means that the signal is inverted or active low, meaning that a low voltage is true and a high voltage is false. AS is the address strobe, indicating that the address pins hold a valid memory address. And the address pins are for the memory address that the request is for, and the data lines is where the data bytes go. This CPU has 20 address lines, so it has 1 megabyte of functional memory space. Internally, the CPU registers are fully 32-bit, but the upper 12 bits of the pointers aren't connected to the outside world. The CPU also has 8 data lines, so it can only access 1 byte at a time. This brings us to another aspect, NDNS. If I have a value that is 2 or 4 byte longs, which order does the byte go into memory? To this problem, there are 3 answers in the wild: the Intel way, the PDP way, and the correct way. The correct way, or big endian, is to store the most significant byte first. So when you read the value in a hex editor, the digits come in the order you'd expect them to. This is how most sane computers historically has done it. The PDP-11 and Intel's 8-bit and later chips, and the clones of them, used little endian, where the least significant byte comes first. There are some theoretical advantages with this, such that a shorter read of a long value still results in the lower bit being correct. This sounds like copium to me, and any sane person can have a quick look at this scheme and tell you that it's stupid. But wait, then there's the PDP-11 way. The PDP-11 stores 16-bit words little endian, but when you store a 32-bit word, it swaps the two words around such that the most significant word comes first. When Intel was out looking for bad ideas, it seems they didn't adopt this one. Anyway, what I wanted to say is that everything was great until Intel ruined everything, and now all modern platforms store their numbers backwards. Rant over. Anyway, the 68K uses big endian, so that's the order multi-byte values go into memory over the 8-bit bus. The first order of business is to write code for my bus probe in order to load actual code onto the computer. So at this point in time, there is no point writing code for the CPU to execute as I don't have a way to load it. I've connected a bunch of the data pin on my parallel port to the bus probe, and the read data comes out on a paper out status line. There isn't really a good API for raw access to the parallel port in this version of Linux, so I instead access the hardware directly. There are some macros and an IO perm call to request permission for IO ports in Linux, so that's all fine. The macros didn't work for me without messing around a bit with them. I think this is a bug in my version of GCC. Declaring stuff as extern inline sounds weird, but it is correct. Regardless, I can access the parallel port now, so I start working on code to push data through the shift registers. At the most basic level, this means putting a data bit out on the line and reading a data bit from the input, then pulsing the clock line. This will push one bit into the shift register, and the next bit at the end will show up on the input line. This is then wrapped in a convenience function that clocks out a whole byte, which is the equivalent of one of these shift registers. Since there is 5 shift registers, I can shift out 5 bytes of data before the data I shifted in starts appearing on the input. There is also a latch call. This will transfer the contents of the shift register to the output pins, or in the case of the last one, load the shift register with what's on the input pins. This way, the output pins won't be spazzing out as you push data through the chain. On top of this, I can build an API to load an address and data onto the 68K bus, toggle the address and data strobe while setting the read-write line low, and that will write to RAM. Reading from RAM can be done in a similar way. The idea is that I should be able to write data to RAM and then read it back. As I didn't map the input data one-to-one to the bus for layout reasons, I do need to shuffle the bits around in software to get the real value back. Now that I've reached the point where I can write a pattern to RAM and read it back, I guess there's no point procrastinating it further. It's time to write some 68K assembler. As a quick primer for those who don't know, M68K is a 32-bit CISC architecture, with 8 data registers named D0 through D7, and 8 address registers named A0 through A7. A7 is the stack pointer, and the rest of the registers are general purpose. There is also a program counter, which points to the next instruction. Actual ALU and computational instructions mainly work with data registers, while data loads and address calculations use the address registers. Anyway, let's get started. A hello world is quite involved, so I'll be starting with something simpler. The first 2 rows here are the reset vector. The first line is the initial stack pointer, which I set to the very top of RAM. The second is the initial execution address, which I set to the address right after the reset vector. I make _start a global symbol, which means the linker can see it, and here I can add my code. But actually, there's really only one instruction I care about. I load the literal hexadecimal byte 12 into the memory address C000. Afterwards, I park the CPU in an infinite loop. The default data length is 16-bit words, so the L suffix to the instruction means long, or 32-bit, and the B suffix means byte, or 8-bit. Hopefully, I'll be able to verify with the bus probe that hex 12 is written to address C000 after I try to run the code. But I had to go on a separate side quest here too, as this version of Object Copy can't produce raw binaries. So I had to write a conversion utility for srec into binary. Srec is a plain text format for describing binary data and was frequently used to burn ROM chips and such. I'll have a use for this later. Anyway, I load my code onto the system using the bus probe, check the contents of address C000, and then briefly release it out of reset. When I then check the contents of that memory address, it is now hexadecimal 12. So it seems I can run code. Cool. The next step then is to get the serial port up and running. So I connect the serial port of my computer to the MFP board. There's a few things we need to do to set up the MFP. So let's have a look at the register map of the MFP. Basically, I need to set up the timers to act as baud rate generators for the serial ports. I want to use the serial port at 9600 baud, and the serial ports are 16 times oversampling, so I need 9.6 kHz times 16 for the serial ports. The timer itself has a minimum prescaler of 4, and it has an inherent postscaler of 2, as the timer only toggles the output on timeout. The input clock is a 2.4576 MHz crystal oscillator, so I'm just gonna try to set up all the timers for that. The first 2 lines select the right mode for all 4 timers to generate a continuous square wave. To get 96 on a baud, I need to divide the incoming clock by 2. Then I need to enable 16 times oversampling async mode in the UART control register by setting the top bit high. Finally, I need to enable the transmitter in the transmitter status register. And with that, we should be ready to go. In this tight loop, I check that the transmit buffer is empty, and if it is, I load the transmit register with a capital U. If everything is working, I should get a steady stream of capital U's in my serial console. So I build and send my code over, switch to the terminal, release it out of reset, and there's a bunch of U's. With this, I can write some code to send a boot up banner instead to greet the user. Which we get. Reading data from the serial ports works in a similar way. We read a status flag to check if there's a byte in the buffer, and if so, we read it. I patch in so that every character I send to the computer is echoed back at the user. And I get that working, which brings us to the last part of the bootloader for now. I want to implement an srec parser, which will allow me to upload new code over the serial port. First, a quick look at an srec file. Each line starts with an S, which is where this file type got its name from. After follows a number denoting what type of record it is. A 0 is a comment, a 1 is a data packet with a 16-bit address, and 9 marks the end of the file. The next 2 characters give you the length of the record in bytes written in hexadecimal, including address, data, and checksum. Then, there's an address field where the length depends on the record type. All records in this example have a 16-bit address. And after that, data follows. Finally, a checksum in which all the decoded bytes are just added together. The code itself isn't all that interesting, but it has the following parts. First, a loop that waits for a capital S followed by a record type it recognizes. If it doesn't recognize the record type, it will just start over and wait for another S. This uses some helper functions like getHexabyte, which grabs 2 ASCII characters and decode them to a byte. This in turn calls getNibble, which decodes 1 ASCII character into a 4-bit value. Finally, getAddress calls getHexabyte twice to decode a 16-bit word. Load S1 takes a data record and decodes it with the calls above to get a byte count and an address and such. The S9 call basically just extracts the entry point from the address field and jumps to it, and that's pretty much it. Now that I have a loader, I need something to load with it. So, we finally get to some C code. I currently don't have a standard library, so I'll be writing all the code myself. With the MFP already set up, I just need to check the same status flags as the loader before outputting data to the serial port. Note here that I just happens to know exactly where in memory the MFP is, so I can just create a pointer to it like this. And this function can then easily be called from a function outputting a string. When I try to compile this, I get some confusing errors here regarding __ main. I don't realize it at the time, but this is just because I'm not linking with libgcc. It's a special runtime function responsible for running all global constructors. For now, I just created my own empty __ main to get my code building. To go with this, I need a linker script, which tells the linker where in memory to put my code. I just grab one of the included ones and modify it. I define this one memory area that I call SRAM and then direct all binary sections to it. Linking with that, we can see how it has put everything at 9000 hex, which is 4 kilobytes up into SRAM. I put all of these steps into a makefile, and I can now generate an srec output for my C code. I tried putting this in my loader, but nothing happens. I spent some time troubleshooting this, and I found 2 problems. One is that I need this pointer to be volatile, as the compiler might cache the value it reads from it otherwise. The other is that GCC defaults to generating code for a 6820. So my CPU crashes on an unsupported instruction. All it took was a flag to GCC telling it to generate code for a regular 68000, and I finally had a hello world. But this means I'm now happy with my monitor program, at least for now. So I head north again to get it burnt onto an EEPROM. This is a type of programmable and erasable memory. You can see the chip through the window. To erase it, you shine a powerful UVC source at it. Back in the day, you could erase these by putting it on a windowsill, but when we tried it recently, we couldn't get it working. Maybe we did something wrong, maybe we now have more of an ozone layer than we had in the 80s or 90s, who knows. But this chip goes into the ROM burner. I had to write some code to generate this image. If you remember when I made the boot board, the address and data lines were all mixed up for layout reasons. This required me to scramble the ROM data beforehand, so the data would be read out correctly in the system. But now, I have a ROM, so I can remove the SRAM boot jumper and put it in my boot board. Okay, so no tricks this time. There's just the 3 boards, no bus probe. I'm gonna turn on the power, we're gonna see a boot splash, and I'm gonna send the Hello World program to it and it's gonna execute it. I hope. So let's start with the power supply. The CPU is in halt. I'm gonna press reset. We got the boot splash. And we got the Hello World. Mission accomplished. And that's it. I think that will do for this video. I got big plans for this thing, so we'll see it in future videos. But check back next week, when I'll try to install a better DOS than DOS and a better Windows than Windows. Until then, thank you for watching.